Let us embark on a journey to understand the world of sorting algorithms, which are efficient ways to organize data. In this video, we will explore some fundamental sorting algorithms including bubble sort, selection sort, insertion sort, merge sort, and quick sort. So, what exactly is a sorting algorithm? It is essentially a method to arrange elements in a specific order, such as numerical or lexicographical order. When we talk about sorting algorithms, efficiency is key. Time complexity and space complexity are important factors to consider. Also, different algorithms have different use cases. Sorting algorithms form the foundation of many computing operations. Let's begin with bubble sort. This algorithm repeatedly steps through the list, compares adjacent elements, and swaps them if they are in the wrong order. This process keeps repeating until the entire list is sorted. The time complexity of bubble sort in the best case is order of n, in the average case is order of n squared, and in the worst case is order of n squared. The space complexity is order of 1. Next, let's explore selection sort. This algorithm divides the input list into two parts, a sorted sublist and an unsorted sublist. It finds the minimum element in the unsorted sublist, swaps it with the first element of the unsorted sublist, and moves the boundary of the sorted sublist forward. The time complexity of selection sort in the best, average, and worst case is order of n squared, and its space complexity is order of 1. Now let us discuss insertion sort. This algorithm is similar to how we sort cards in a hand. It builds a sorted array one item at a time, shifting elements to make room for the new element. Insertion sort is very efficient for small or nearly sorted datasets. The time complexity of insertion sort in the best case is order of n, in the average case is order of n squared, and in the worst case is order of n squared. The space complexity is order of 1. Here is a comparison of the simple sorting algorithms we have discussed so far. Bubble sort, selection sort, and insertion sort all have a time complexity of order of n squared, but insertion sort can perform better for nearly sorted data. All three algorithms have a space complexity of order of 1, meaning they require minimal additional memory. Bubble sort and insertion sort are stable, while selection sort is unstable. Simple sorts are best suited for small datasets and educational purposes. Now let's delve into merge sort. It is a divide and conquer algorithm that divides the array into smaller subarrays, sorts them recursively, and then merges the sorted subarrays to produce the final result. Merge sort has a time complexity of order of n log n, a space complexity of order of n, and it is a stable sorting algorithm. Now let's take a look at quick sort. Like merge sort, quick sort is also a divide and conquer algorithm. It selects a pivot element and partitions the array around this pivot, such that elements smaller than the pivot are on one side and elements greater than the pivot are on the other side. Quick sort then recursively sorts the subarrays. The best and average time complexity of quick sort is order of n log n, but the worst case time complexity is order of n squared. The space complexity is order of log n, and it is an unstable sorting algorithm. Here is a comparison of the two efficient sorting algorithms, merge sort and quick sort. Merge sort guarantees order of n log n performance, but requires extra space. Quick sort is generally faster in practice, but it can degrade to order of n squared in the worst case. Merge sort is stable, whereas quick sort is unstable. Here is a visual representation of the performance of the sorting algorithms that we have discussed. Bubble sort, selection sort, and insertion sort all have a time complexity of order of n squared. Merge sort and quick sort have a time complexity of order of n log n, making them more efficient for larger datasets. When should you use each algorithm? Simple sorts are suitable for small datasets, educational purposes, nearly sorted data, especially insertion sort, and situations where memory usage is a concern. Efficient sorts are preferred for large datasets, production environments, when performance is critical, for external sorting, merge sort, and when stability matters, merge sort. Let us recap the key takeaways. Simple sorts with a time complexity of order of n squared are easy to implement but inefficient for large data sets. Efficient sorts with a time complexity of order of n log n are essential for production software. Each algorithm has specific use cases and trade-offs. When selecting a sorting algorithm, we must consider time complexity, space complexity, and stability. For further learning, you can refer to resources such as Introduction to Algorithms, visualgo.net for algorithm visualizations, Geeks for Geeks, MIT OpenCourseWare, and coding platforms like LeetCode. Understanding sorting algorithms helps build a strong foundation in computer science and algorithmic thinking. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.